Okay, so today we're doing lab 12 about looking at the physical layer. And the main idea of today is we want to see when you punch a key on your keyboard, how does that actually get transmitted? What does it actually look like if you were to, get down to the lowest level and look at wires and electrical signals, that kind of thing. Some of the important takeaways, as you see at the top of your lab, on today's lab, normal voltage on the wire is going to be low. A 1 bit will be a low voltage pulse and a 0 bit will be high. We're going to have ASCII characters is basically what we're going to be transmitting today, and those will be 8 data bits. They're going to look like they're in reverse order. We'll talk about that, least significant bit first. They're going to have a start and stop bit like you talked about in class. You have to have a way if you're doing asynchronous transmission, which we're doing today. You have to have a way to tell the receiver, hey, heads up, here's some information coming. And the start bit will be 0 bit, so it'll be high in terms of it'll look like the signal goes high, and a 1 bit will be low. Okay, so again, the whole idea here is to see what would these signals actually look at the lowest level inside a cable when we're trying to transmit them. So the first part of your lab talks about some hardware setup. Good news, did that for you. And so you're not going to have to go through all that. But one thing, just as a reminder, if it's been a while since you've looked at an Oscilloscope, a couple of things. One is down to the bottom left on this display, you see 100 millivolts. That is the vertical size of each one of those boxes. And then in the middle, 250 microseconds means that as the width of each of those big boxes is 250 microseconds. Okay. Now on your display here, if you're watching this Panopto, you have 2 displays you can switch back and forth between. The main display you should be seeing now is the oscilloscope, and then there'll be another display which will show the screen where we're actually putting in the commands. So everything's set up here, and so we can move on to the next page. Again, the way we're actually going to do this is something called TerraTerm, which is a program that allows us to kind of get down at the low level. And just one thing I wanted to show really quick is, somehow I have to have a way to connect wires to what's going on in my computer. A little bit hard to do, but we have something here that basically treats a USB, it uses a USB port and makes it into a serial port. So we have these wires that then are connected in and going all the way back to look at the oscilloscope. And let me see if I can get that back nicely for the rest of the session. Hope nobody's getting sick here. Okay, I think that should be pretty good. Okay, so that's how we're actually going to see these signals that you usually wouldn't be able to see is that special little adapter there. So we have it all set up. If you're watching on Panopto, if you go over to the other screen, you'll see that we have something called TerraTerm. Again, this is the software that's going to let us do that. The setup, we're using a serial port. And so these are all the settings for the serial port. So these things should make some sense to us now. Now the port, don't worry about that. That's just particularly our USB port. But 9600 is the baud rate. That's how fast symbols, in this case zeros and ones, are transmitted. And it's equivalent to bits per second for our case because we're doing 1 bit with each symbol. It talks about whether or not we have the data, the actual data we send. Well, we're sending ASCII characters. ASCII characters 8 bits. So that's the actual data we want to send. Parity is something used for error detection. We're not doing that. Stop bits, we do have those. So we're going to have a start bit and a stop bit, and that's there. And something called flow control, which we're not using. So that's the setup for that. And the one thing I'm going to do here is I'm going to set up my terminal for something called local echo. That just means that way I get to actually see the keys that I'm typing. All right, we're flying through this lab. You are all the way down to part 3, so we can actually get communicating. If we were back at the Naval Academy, you would be doing this all yourself. You can thank us later for setting this up for you. Okay, so what we're going to do is, when you think about it, a signal on a wire, it's especially at this level, it's changing pretty fast. What we need to do is set up our oscilloscope to basically take a snapshot when this thing changes. So I'm going to do something called single sequence, which basically sets it up to wait and say, once you do something, I'll do it. Okay, so over in my tera term window, the very first thing I'm going to do is I'm going to type the lowercase m. And there we go. Something popped up on our oscilloscope when we did the lowercase m. And we're going to look at this a little bit more later, but we get a sense of how wide the bits are. So it looks like something right, that first one looks like the width of the bit. Okay, so the next page of the lab is kind of going to break down for us so we can see what this looks like is, what's this mean? What's going on here? How does this correspond to things that we've seen? So if you look at the diagram at the top of your lab, what's called page 245 on your lab, a couple of things that it's showing you here. First off is the default for this, when nothing's being transmitted, it's at that low level. Okay, now something that might seem a little counterintuitive to you, but for our setup here, that actually corresponds to what would be ones. So the binary 1 is the low level, and the binary 0 bit is the high level when it pops up. Okay, so the start bit then is when it goes up to a 0. Okay, we said at the beginning of the lab, the start bit is always going to be the opposite of the default. So if the default, as in this one, is that low level, which corresponds to a 1 bit, in order to tell the receiver, hey, guess what, you're about to receive some interesting information, we do the opposite. So that first bit that pops up there is what we call the start bit, and that's just say, heads up, you're about to get something. That means that the next 8 bits are the actual data that we get. So it's that 1 0 1 1 0 1 1 0. Again, the zeros are whenever they go high, and the ones are whenever they go low. One thing you'll notice is that when you have 2 ones in a row, that just means that it holds that level for that twice amount of time. And then the stop bit is always the opposite of the start bit. So the stop bit's going to be a 1. Now, since there's no signal after the stop bit, you don't really see the 1 too well, but the 1 is there. Okay, what does this mean? Well, now we look at the bits transmitted. If you look at that diagram below, so it looks like our bits were 0, 1, 0, 1, 1, 0, 1, 1, 0, 1. Well, the first thing was a start bit, so that's not really part of our data. The last thing was a stop bit. That's not part of our data. So the data bits are those middle 8. And one thing that might seem interesting to you, but we actually need to flip them around. So this is down to that first note. It says, when no transmission occurs, voltage is low, only goes high when the start bit appears. If you look up lowercase m in the ASCII table, so there's a link there, it sends you to an ASCII table. It's kind of a nice one for this lab because everything's done in binary, so you don't have to do hex to binary conversions. But what you would see if you look up lowercase m is that it should be 0110 1101, which is the reverse of what we've transmitted. So here's essentially what's going on here is we're writing it the flip way, because this is sort of the way that the receiver would receive it. They would receive that least significant bit first and the most significant bit last. Okay, so that's as it shows you. If you reverse the data bits, then you get to what would be the lowercase m on the table. Okay, you still haven't had to do anything yet, have you? You're just listening to me. But we're about to have you do a little bit of work here. So I'm going to hit single sequence to get it ready one more time. And I am now going to do question 1. We're going to type the lowercase u over in tera term. Lowercase u. There is my new signal. Now, it's up to you. Well, the first thing is you want to do is draw a rough sketch of the waveform. Now, one thing to remember, you have 8 bits of data plus a start bit and a stop bit. So there are a total of 10 bits here as you draw it out. So you want to do a good sketch on your answer sheet. And what you want to do is a couple of things, as you see in the question. One is specify which ones do you think are ones and which ones are zeros. If you're confused, you might go back to our last example and see which one, how we did ones and zeros. Also figure out which ones are the data bits and which ones are the start and stop bits. If you want to annotate that on your diagram, that would be good. We're not quite interpreting anything about the data yet, but you are just drawing this and then labeling with each one, whether it's a 1 or a 0, and then what are the start and stop bits. And hint is you should have a total of 10 bits, 10 zeros and ones. Okay, so now compare those bits you've seen on the Oscilloscope with the ASCII table from that website we pointed out earlier, and determine if they match the lowercase u. Hint, if you go, man, they seem like they're exact opposite, well, then go back up to what we did with the lowercase m in the previous example, okay? All right, so if you've done that, feel free to pause, come back. Now in question 3, now we're going to do a capital U. Capital U. That did not work. Don't do anything yet. I did not do my stop sequence, my single sequence, which says get ready to take a new picture. Now I got to come over. There you go. There's your new picture that you're working with for question 3. By the way, do remember lowercase and capital are different on your ASCII table. It does matter. Similar to what we did last time, draw a rough sketch, specify which bits you think are ones and which ones are zeros, indicate which ones are start and stop, and therefore which ones are also the data bits, and then again compare to the ASCII table and see if they match once you've done that reversal, okay? So all that is part of question 3. Okay, question 4, just for good measure. Let's do it one more time. But one thing to notice here is that you know, we have things beyond just letters on our ASCII table. We have things like the tilde. So if I type the tilde here, that's not a tilde. Ignore that. Turns out I need to do shift. Okay, so let's try again. Ready, shift, tilde. There's the tilde. Okay, there we go. That's our tilde. And one more time, draw a rough sketch of the waveform you transmitted on your answer sheet. Specify the corresponding bits you believe them to be ones or zeros, which bits are data bits, which are start and stop bits. And as for the last time, compare the bits you see in the ASCII table and ensure they match. Okay. One thing you'll need to come back to over here is if you're finding that it's not matching, make sure that you have a total of 10 bits. Now remember, one of the things about this is the width of these things does matter. So for instance, the one that still is on the screen, notice that that first pulse is twice the size of that second pulse. That means you actually have 2 bits with that first pulse and only 1 with that second, okay? So in question 5 actually gets to that a little bit. It says the horizontal axis, the time axis, should be set to 250 microseconds. It is. And each of the blocks on the display is 250 microseconds wide. Now that is the whole big block is 250 microseconds wide. For the tilde character, estimate what the duration of 1 bit is for this transmission. That is, how wide in seconds is 1 bit. Now here's where you have to be careful again, is remember the smaller one is 1 bit. That bigger one is a total of 2 bits. Now, in terms of measuring, it might be easier because to measure the first one and divide it by 2. So that first one we know is 2 bits. Let's see if we know that the whole big block is 250 microseconds. And now you see those dots, those little dots that are in each block, break each block into 5 smaller portions. So if you know the big block is 250 microseconds, you can find out how wide then is it between 2 of the smaller dots. And then once you know that, you can figure out the width of the large pulse, and that is 2 bits. Then you can go from there to figure out the width of 1 bit. Okay, so your answer should be, in terms of time, the width of 1 bit. Okay. So now your answer to question 5 is about how long a bit lasts in seconds. So now you want to get to the all-important aspect of bit rate. Okay, bit rate is how many bits per second are being transmitted, and you want to calculate the bit rate for this transmission using your answer to question 5. By the way, bit rate is hugely important. You pay money for bit rate. That's the way that Verizon and Comcast and Sprint and all those folks compete. That's one of them, is the kind of bit rate they can get you. And when you graduate and you go to set up internet in your first apartment, one of the things you'll be looking at is different data plans. And one of the selling points is what's the bit rate you need, how many megabits per second. So calculate that for question 5. Okay, so everything we've done so far has just been kind of big or single characters at a time that we've typed. Turns out we can actually also do a whole file. So we have a file. It's called us.txt. By the way, again, if you are on Panopto, you can switch back and forth between the two screens. If you look at my other screen, I'll open up us.txt. It is opening. Let's see what's in it. Suspense builds. While we're letting that small file open, which shouldn't take that long, you'll notice that what we're going to do is we're going to, once we do this, we're going to be able to download that file, or sorry, run it through Terraterm. And oh, by the way, before I forget, question 6, you actually do know, okay, so here we go, let's put this back over here. Very, very impressive file, capital U, lowercase s. All in one thing there. Okay, there we go. Let's see what we're going to do here. Question 6, you can check your answer because earlier when we set up our terminal, we set up a bit rate in terms of it's called the data rate or the baud rate. So you should be able to check your answer. Okay, let's see. Move the small arrow on the top display. Okay, so now what we're going to do is we're going to go back. We're going to move our horizontal position here so that we can see everything when it happens. Don't want to miss a thing. Moving it all the way over here. So again, this is making now the 0 time to be the far left of the display. We're going to put a single sequence to get ready for our next thing that we do here. So now over my Terraterm window, I am going to go to send a file from the drop-down menu, which is under File. There we go, File, Send File. And it's going to ask me which file I want to send. I am going to go to my, let's see what we've got here. Let's just copy and paste my, it won't let me do that. Let's see, one moment here. Okay, long time to get there. All right, it has sent it. Okay. For sending this file, how many bits were transmitted? Write out the stream of bits transmitted, including start and stop bits. In your stream of bits, indicate the ASCII characters. Okay. So you should see a bunch of bits here. Now note that you should have a start bit at the beginning and a stop bit at the end. You have data in between. Okay, so the data is the in between, and it should be those 2 ASCII characters. You should be able to confirm that. So that's question 7. Question 7, we're not asking you this time to necessarily sketch it, but you can just write out what the bit stream should be. Question 8 asks you what type of line coding is used in this lab. And then question 9, okay, now here's one that you don't have to even use the video anymore. Using only the transmitted voltage pulses and the screen capture shown in the figure below, determine the ASCII characters that have been transmitted. So this one, you're just reading it off right there. Okay, that's it. I hope you enjoyed a look at the very, very, very low level of how keystrokes are encoded when we're sending them across a wire, and it only goes up from here.